Imagine that you have been given the task to estimate what is the proportion of lefties in the United States, or the average number of miles driven daily by US drivers. Because the populations of interest, in this case the United States population and the population of United States drivers, respectively, are so large, made by millions of observations, we need to resort to an expedient in order to estimate these population parameters. Inferential statistics is defined as the process of making estimates about population parameters using a sample drawn from the population of interest. At this point, it is important we understand the fundamental differences existing between a population and a sample. As defined during our first lesson, a population consists of the total number of observations in a group. The population often can be very large. For example, consider population of US adults, or the population of fish in a lake, or the population of objects being produced by a manufacturing plant over a year. At times, as it is in the case of a process, a population can be virtually infinite. When a population is so large and dynamic in terms of composition, it is often impractical, if not downright impossible, to characterize it. A population is described by parameters, such as the population mean, mu, and the population standard deviation, sigma, for quantitative variables, or the population proportion p for categorical variables. Conversely, a sample can be quite small, although the larger the better in terms of statistical precision, and it is described by summaries, such as the sample mean and the sample standard deviation for a quantitative variable, or the sample proportion for a categorical variable. We call such summaries statistics. But sample size considerations notwithstanding, a sample must be representative of a population for the inference on the population to be statistically accurate. A representative sample must be free of biases. And there are many types of bias, but the following three are the most important ones. A coverage bias, also called a selection bias, occurs when certain subgroups or portions of the populations are either overrepresented or underrepresented in the sample. For examples of selection bias, just consider the most recent presidential elections, when statistical polling companies grossly misjudge in their samples what would have been the actual voters' turnout at the booths. There are many types of selection bias, but for the purpose of this class, we shall not delve any deeper into the topic. The other two types of bias deal with surveys. The non-response bias occurs when the respondents differ significantly from the non-respondents. This is an issue well known to any university instructor who reviews the students' course evaluations at the end of the semester and realizes how only those students who had something really good or something very bad to say about the course completed the course evaluation. Then there is the response bias, which occurs when a questionnaire is phrased in such a manner that it unfairly influences, and therefore biases, the respondent. As an example of response bias, consider the times in which you may have participated in a survey where you have felt compelled to give answers that are socially acceptable, and by so doing, not given truthful answers. In inferential statistics, it is fundamental that we adopt sampling techniques that prevent any form of bias. One sampling technique that minimizes the possibility of a selection bias involves the random collection of a sample from the population of interest. In such a randomly collected sample, it can be assumed that each of the population's observation has the same probability of being selected for the sample. When a sample has been collected randomly from a population, we say that the randomization condition is satisfied. And when such randomization condition is satisfied, we can assume the sample to be representative of the population. There are several random sampling methodologies, and for the purpose of this course, let's consider a few. The simplest and most straightforward of sampling techniques that yield a representative sample is called simple random sampling. However, in many cases, especially when the population is quite heterogeneous and made of profoundly different subgroups, we need to create a simple random sample for each of these subgroups and pool the sample together into a single one. We call these subgroups strata, and the sampling technique stratified sampling. Another popular random sampling methodology among statisticians is cluster sampling. Cluster sampling is often used when conducting test markets. The trick is to find one or more than one cluster in a large geographical area, such as the United States, that has similar characteristics to the overall population. For example, consider a metropolitan statistical area with the same market shares among its main competitors and demographics as the national average. A company interested in testing a new product may choose to deploy a test product only in such geographical area, and then make an inference about how this product will fare across the entire United States. Finally, we have systematic sampling, in which we systematically query the 10th or the 15th or the 20th person coming out of an establishment to ask a question of interest. This is the sampling technique usually employed for exit polls during elections, because the order in which voters leave the voting booths is, in fact, random.